Okay, today we are going to talk about section 9.2, which are parametric equations. Let me just tell you, this is a prerequisite to two-dimensional motion, which we'll be going into. We're actually not working with any calculus today. This is just a new way to sort of plot points, which is going to lend itself to working with vectors and things down the line. You don't have to worry about that today. The thing you have to worry about today is just the parametric equations. Okay, so first of all, the way parametric equations work is we have there's still a rectangular equation, or excuse me, a rectangular curve where we have an x location, which is the horizontal, and a y location, which is a vertical. The difference is, in the past, what we've worked with is either we had a function of x or a function of y. So we either had a function that that was input x, output y, or vice versa. You know, and we dealt with things that weren't functions of either, but generally we were given one equation that links x and y, and that's the relationship we would graph. With parametric equations, it doesn't work that way. For any point x comma y, we have a distinct function of t, okay? So x is equal to its own function of t, y is its own function of t as well. And so this is a little bit of a different situation. So what we're going to do today is we're going to start off by sort of graphing what these things look like. So this is our first parametric equation. I want to show you what this thing looks like. And then what we're going to do is we're going to remove the t and get sort of the normal equation that we talked about. Some wording that you'll hear me talk about, I'll talk about Cartesian. That's not a word that came up before. Cartesian is the typical x to y relationship. So in the past, when we just had like y equals x stuff or x equals y stuff, that's Cartesian. This is parametric, okay? We haven't really needed a name before because we didn't do anything other than that. Okay, so now we have x is equal to its own function of t and y is its own function of t. So we want to see what this thing's going to look like. So basically what we're going to do is we're going to plot these points first. Now I will tell you that when we come to class, I will show you how to do this on your graphing calculator. Today I want to do these by hand. Okay, so let's go ahead and get these. So these are really easy to calculate. If I plug 0 into x, I get 0, 1 I get 1, 2 I get 4, 3 I get 9. So those are the x locations, and they still refer to the relationship horizontally. Now I'm going to do the same thing with the y equation. So 0 goes in, I get 6. 1 goes in, I get 3. 2 goes in, I get 0. And then 3 goes in, I'm going to get negative 3. So when I plot these, I'm plotting points, for instance, 0, 6, 1, 3, 4, 0, and 9, negative 3. So even though t is the independent variable with both of these, t is a hidden variable. I don't see it like I see x or y in the normal Cartesian equation. So 0, 6 is right here. Okay. 1, 3 is right there. 4, 0 is right here. And 9, negative 3 is right here. Now, I'm just going to go ahead and connect these dots. I will tell you that if we kept going more points, this thing would continue on, and maybe we'd even start to see what type of shape this is. Right now, it's hard to tell. Okay, so just a couple things. One thing that we want to get used to is, in a case like this, if I was looking at t going from 0 to 3, right? This is what we would call the initial point. This would be called the terminal point. And we do want to indicate the direction. So in a normal equation, we've never done this before, and the way I tell direction is as t increases, what direction was it going into? So it was going in this direction, so I indicate that with arrows. So a little bit different than what we've seen with our typical Cartesian equations. So this is a parametric graph. So now at this point, what I want to see is what the actual normal equation is. So in a case like this, it's really easy to do this. And basically, what you do in a normal case like this is we're going to solve for t either here or here. Either one would work, but let me point out, if I solve for t here, I then would have to have plus or minus, and I really don't want to deal with that. So instead, I'm going to solve for t in this equation. So let's solve for t in this equation. So what we're going to get is, let's see, Sorry about that. So it's going to be y minus 6 divided by negative 3 is equal to t. So t is equal to, let's see, negative 1/3 y plus 2. And you know, simplification in this type of scenario doesn't really matter. And so what I'm going to do to get my equation is I'm going to plug this in for x. So this equation goes here, so I get is negative 1/3 y plus 2 squared. I'm not going to bother, you know, foiling that out or multiplying it. And this is my Cartesian equation. Now, without getting into too much detail here, basically what we have is x equals a y something squared. So if we had a y equals x something squared, we all would know that that is a parabola that either opens up or down depending on the scenario here. So in this case, since if I multiply this out, I have a positive y squared. So instead of opening up like something positive x squared, it's going to open to the right. So this equation, the actual Cartesian equation, basically becomes like a container for this thing. So it's going to be something like this if we continued on. And if we started plotting points, for instance, if we plugged in if we plugged in t equals -1, you would start to see it sort of turns this corner. So the thing we have to understand is this equation gives us sort of the general shape in which that's going to go, but it's not the same thing. So for instance, you know, because we know, for instance, here, this is at t equals 0. This point is at t equals 1, etc. So we have this sort of lurking hidden variable throughout, and that is parametric equations. Okay, I'm going to do a few more examples here today, and you know, that's basically going to be our investigation. Okay, example 2. Once again, we're dealing with parametric equations. X and y are defined separately, and now we're going to go ahead and calculate our points here. -2 goes into this, into x, and we get 4. -1, we get 1. 0 and 1. Excuse me, 0 and 0, 1, and then 4. And now let's do the y's. So that's going to be -8. Keep in mind odd powers retain the negative. This will be -1, 0, 1, and 8. So let's plot these points. So we have 4, -8. So this part we plot just like always, 4, -8. Okay. 1, -1. 0, 0. Okay. Then we have 1, 1. And then 4, 8. And we get something that looks like this. So if I'm looking at this from just, fingerprints all over this, if we're looking at the t goes from -2 to 2, okay? This is our initial point, this is our terminal point, and notice we're going in this direction. So we're getting kind of this curve thing, and then in the opposite direction. Okay, so there you go. Oh, another thing I want to point out that is a little bit confusing. So in the past when we talked about functions of x or y and we got a graph like this, if this was, for instance, well, it's not a function of x, but if we looked at it as a function of y, the input for y would go from -8 to 8. We would see that in the graph. You do not see domain and range when it comes to a parametric equation, right? The domain is basically what are the possible t values. So in this case, the natural domain, any t value is possible. So the natural domain would end up being all reals, okay? Now here I'm just looking -2 to 2. So something to keep in mind, we can't just look at a graph and tell the domain anymore because we have this hidden variable t, which is actually the independent variable, which indicates what the input is. Okay, so that's basically the graph. Now once again, let's take a look at what this would look like if we looked at the actual normal equation, the Cartesian equation. So I'm going to solve for 1. Once again, I'm going to go ahead and solve for t in this one because since that's an even power, I would have to do the plus or minus. Odd powers you don't have to worry about the plus or minus because the odd powers, of course, retain either the positive or the negative. So let's solve for this one first. Okay, so what we get is t is equal to the cube root of y, all right? So then x is equal to the cube root of y squared. You can express it like that, or realize that this is a fractional exponent. x is equal y to the 2/3. And once again, this is a function of y, it's not a function of x, right? It passes a horizontal line test, it does not pass a vertical line test. So this would be our normal equation, okay? Okay, a couple more examples here. Okay, example 3, we're going to get into some trig situations. At the front of this isn't going to be much different than what we did before. When we actually solve for the normal Cartesian equation, we're going to have to do some adjustments here. Even though these are all special values, you know, I will say that, you know, grabbing a calculator just to know what this is as far as the decimals here is fine. I don't have a problem with that. So let's go ahead and take a look at this. So let's go ahead and plug in negative pi over 2 into x. So negative pi over 2 plugged into cosine is 0, so obviously 4 times 0 is 0. Negative pi over 4, if we plug that into cosine, that is going to be radical 2 over 2. Radical 2 over 2 times 4 will be 2 radical 2. Okay, and like I said, we'll go ahead and calculate that. 0, well, cosine 0 is 1, so that's going to be 4. Pi over 4, it's going to be the same as this because the cosine is still positive radical 2 over 2, so that'll be 2 radical 2. And then finally, pi over 2, we're at 0. Okay, we're going to do the same thing with y. So negative pi over 2, well, actually, we're at the bottom of the unit circle. That means sine is negative 1, so that will be negative 5. Negative 5, or pi over 4, would be negative radical 2 over 2. So that's going to be 5 times negative radical 2 over 2. So that'll be negative 5 radical 2 over 2. And there's really nothing I can do with that as far as simplifying. 0 goes in, that's just going to give us 0 here. Pi over 4 will be the same as this, but positive 5 radical 2 over 2. And pi over 2, that's back to 5. So let's just, for the sake of you know, normally we do 3 decimal accuracy. There's definitely no point in doing 3 decimal accuracy here. I would just round to the nearest 10th place. So here I get roughly 2.8. So this would be 2.8. And then on this one, let's see, 5. Now it's 2.5 times radical 2. So this is roughly 3.5. So this will be roughly negative 3.5. This will be positive 3.5. Okay, so let's go ahead and plot these points. So 0, negative 5 are right here. Okay. So that's our first point. Oh, and by the way, they're giving you the domain. 2.8, which is somewhere in there, to negative 3.5. So yeah, right down there. Oh wait, 1, 2, 3. Okay, counting is problematic. So that point goes right there. Okay, 4, 0, right here. 2.8 and 3.5. So that goes right about here. And then finally 0, 5. And then once again, this is our initial point at negative pi over 2, and our terminal point. We're going to connect this. And we're moving in this direction. This might seem familiar to something we've done before, and I'll talk a little bit about this when we're done. Okay, so that is really no different than what we did before, except of course, you know, we did decimal approximations for the values. But other than that, it's exactly the same. So the problem is when I actually solve with the other ones, I could solve for t, no problem. Here are the parameters theta, which is you know, refers to the angle measurement, right? So what we're going to do here instead is we can't just solve for theta here because then we'd be using like arc sine or arc cosine. The problem with arc sine and arc cosine is the domain then becomes that limited domain. So whenever we get one of these, what we have to do is we have to find a way to use trig functions. And I will tell you, there's not going to be too many, but one of the things that comes up quite a lot, and is the case here, is sine squared theta plus cosine squared theta is equal to 1. There'll be other ones where we use like tangent to sine over cosine, but there has to be a way to write this. So for instance here, I can use this here if I just solve for cosine here and sine here. So this is going to be, let's move down here, x over 4 is equal cosine theta, okay? Y over 5 is equal sine of theta. Now, I'm in business, because what I can do is, I can square both sides of this, and the equation remains balanced, right? So these are still true if I square both sides, okay? So what I end up getting is x squared over 16 is equal cosine theta squared. Okay, so now what I can do is realize that this is equal to this. So I can add the x squared over 16 to this side, and I can add the cosine squared to this side, and it's going to remain balanced. So here, let me move over here. Sorry about this. I know at the bottom you start getting cut off. So what I'm going to get here is I'm going to get x squared over 16 plus y squared over 25, which is equal to sine squared theta. Yep, let's give myself more room here. Not doing a very good job with this. So let's see, x squared over 16 plus y squared over 25 is equal to sine squared theta plus cosine squared theta. All right, but anyways, what's sine squared theta plus cosine squared theta? That's equal to 1. So now I have an equation that will give me all the possibilities. Now, something that really I don't care if you know or not, this is what's called a conic section, and specifically, it's an ellipse. The x value on either side. So if this thing kept going around, like if we look at this entire equation, it looks like this. You don't need to know that this is a conic, but it is a conic, and it is what's called an ellipse. The x would be -4 to 4. You take the square root of this, and the y would be -5 to 5. Okay. Now, as I was talking about, it might be ringing a bell here that you realize at this point, hopefully, that the unit circle is actually a parametric equation, right? So think about what the unit circle is. X equals cosine theta, and y equals sine of theta. So here, we had the same thing. Notice it goes in the same location. So this is just a parametric equation that you've been working with, I don't know, going back to geometry or algebra 2 at least. By the way, if you flip the cosine and sine, it still gives us a circle, but instead it moves in the opposite direction. All right, just 2 more examples today. Okay, so example 4, same type of thing. You're going to think, this is going to give us a similar thing. The squaring actually changes things quite a lot, which we'll see in a second. So let's start off with x. So negative pi over 2 plugged into that is going to give me -1, but then we're squaring it, so that's going to be -1 squared, so that's just 1. Okay, negative pi over 4, so that's going to be negative radical 2 over 2, and then we're squaring that, right? So that's actually going to end up being a positive, and that's going to be 2 over 4, so that's 1/2. By the way, we know if we plug pi over 4 into that, we'll get the same thing, because pi over 4 will just be positive, but squared, we're going to get 1/2 again as well. If we plug 0 into that, that's just 0. 0 squared, of course, is 0. Pi over 2 gets plugged in it, that's 1. That's 1 squared, and there you go. So that is the x done. Let's look at y. Okay, so y is just cosine squared theta. So negative pi over 2, that is our 0. Negative pi over 4, once again, that's just going to be negative, or actually, positive radical 2 over 2 squared is going to be the 1/2. 0 squared, 0 goes in, I get 1. 1 squared is 1. Pi over 4, radical 2 over 2, radical 2 over 2 squared is 1/2. Pi over 2, we're back to 0. So let's go ahead and plot these. Obviously, I'll just do 1/2, 1. And I guess we're just up on the top half. 1/2, 1. So let me mark that. 1/2, 1, 1/2, 1. So let's plot our points. Okay, so 1, 0 is right here. 1/2, 1/2 is right here. 0, 1 is up here. And then we actually go back the other direction. 1/2, 1, 0. This thing will actually just bounce back and forth, right? So it's got its initial point and terminal point are the same. So it starts moving in this direction. And then it flips back in the opposite direction. So it's actually multi-directional depending on what our p value is. Okay. All right, one last example, and that will be it. Oh, I'm sorry, stop. I forgot. We need to write this as a normal equation. Yeah, I guess you got the point anyways. Sorry about that. All right, now that's really ugly. Okay, so this one's actually really easy because it's ready to go. Realize that I have x equals sine squared theta, and I'm going to use exactly the same thing on the other side. Since y is equal to cosine squared theta, I can add y to this side, and I can add cosine squared theta, and since those are equal, this equation will remain balanced. So I'm going to get x plus y is equal to sine squared theta plus cosine squared theta. And this, my friends, is just 1. Okay, so we get x plus y is equal to 1. And you can see that makes sense. It's just a line here, right? Now, of course, this equation continues on, right? So just important to keep in mind, these and these are not the same thing at all. They have the same kind of image, but you know, I actually think of it this way. I don't know if this helps or not, but if you think of like sparklers in summer, okay, and you move a sparkler very dark in front of you, what happens is in real time you can see the sparkler at any point, right? So that's like the parametric equation. But then if you take the sparkler down, you still see that image, right, of that. You don't see the individual points where the sparkler was, but you see where the whole path of the sparkler. So that kind of gives us the path, and this gives us sort of the location of this thing in any particular spot. So not necessarily a great analogy, but it's important that we realize that these things are not the same thing. And now we'll do one last example. Okay, final example for today. So basically, they're giving us, they want the graph to look like this. This is our sort of normal equation, but they're setting the parameter. One thing you want to understand is, big difference here. We have this equation that gives us a line. We can maneuver things, but generally it's always going to be equivalent to that. I can have an infinite number of parametric equations that would have this graph, would have that image, but would be completely different. And that's kind of the point here to sort of understand. So once again, it's sort of contrasting this idea of a typical Cartesian equation, what we've been working with so far, that's just x and y in the relationship, and a parametric equation. All right, so it can't get any simpler than this. T is equal to x, so that means that x is equal to t, which means that y is just simply equal to, instead of x's, we've got t's here. This is it. It's just 4t minus 3. I'm done. So that's one way I can describe this thing. Okay, we'll graph these in a moment so we can talk about the difference. We know what the general graph looks like, but we want to see how that compares. Now this one's a little bit harder, right? So we'll get x equals add x, t, so that'll be 2 minus t. Okay, so now I've got to get the y, so I'm going to take this and plug it in for x here. So not very difficult. Okay, but these are going to be different, which you'll see here in a moment. So this will be 2 minus t, and then minus 3. Now, I'm going to go ahead and simplify this for the sake of simplicity. So let's see, this will be 8 minus 3, so that's 5. So 5 minus 4t, okay? All right, so now this is my parametric equation. Parametric equation here, different from the parametric equation here. Both are going to have that as their sort of post image. Like I was talking about, if we're talking about the sparklers, excuse me. Both of them are going to have that, when I take the sparkler down, are going to have that image. But let's see how they're different. So basically what I want to do is just like what I did before, but I just need a couple points. I know this is going to be linear, so let's just do 2 points for each. So here we'll do t, x, y, and let's just do 0 and 3. Okay, so let's just leave it really basic. Okay, so obviously this is 0, this is 3, this one's super easy. And then y, 0 goes in, that is negative 3, and 3 goes in, that is 12, that's 9. Okay, so that is my first one. And let's give that a quick plot. I don't care too much about the details. So 0, 3, we'll write about in here. And then, I'm sorry, that was 0, negative 3. I'm not looking at this right. So 0, negative 3 is our first point. Okay, it's down here somewhere. So we'll just call that 0, negative 3. And then 3, 3, 9. Over here somewhere. So this point is 0, negative 3, and then 3, 9. Now, this was at t equals 0. This is at t equals 3. So this thing, if we're doing the whole graph, is moving in this direction, right? As t increases, we're moving in that direction. All right, let's take a look at this scenario, okay? So in this scenario, same thing. We'll do x. So just the same points to contrast them. So go 0, 3, and x, y. Okay, so 0 goes into x, we get 2. 3 goes into x, I get negative 1. All right, 0 goes into y, we get 5. 3 goes into this, we get negative 12, so that's negative 7. Okay, so our 2 points are 2, 5, and negative 1, negative 7. So let me do this graph again. Once again, I don't really care much about the details. I'm just contrasting that these are different. Okay, so at 2, 5, I'm in here somewhere. Okay, same general shape, 2, 5, so this is t equals 0. And then here we're at negative 1, negative 7, so somewhere down here. Okay, so same shape, but let me point out, at t equals 0, this one we're here, this one we're here. At t equals 3, this one we're here, this one we're here. It's not the same thing. And by the way, this one's moving in the opposite direction. From t equals 0 to t equals 3, as t increases, we're moving in that direction, and that is my parametric equation. So they both have that sort of post image of y equals 4x minus 3, but they are different equations. So that's parametric equations. We're going to start off by just investigating with parametric equations before we get into the calculus. I will tell you the thing that it's not hard. It's definitely pre-calculus stuff, even though you haven't seen it before. It's just very different than the way we've been dealing with sort of the normal x input or y input. Usually x input, and this is. We have x and y are now both the outputs for this other variable t. And so this is parametrics. Once again, we spent a lot of time plotting points today. We're going to do a little bit on the front end. I will tell you down the line, we don't do a lot of plotting points of parametric equations, maybe just a little bit. Certainly we wouldn't be doing that on the AP test, but I do think it's important at first to sort of plot points. Now, your calculator does have the ability to do parametric equations. If you want to try to explore with that a little bit, feel free. I will show you that on class when we have class. I'll definitely show you how to do that. But that's about it. So that's parametric equations, and this is starting our investigation for Chapter 9.